Everyone, we're here at the MRI Wasteman Center's MRI scanner facility, and this is a scanner demonstration for everyone. Unfortunately, you guys, given the current COVID situation, we're unable to have you come and see the scanner. Just going to give you a brief intro layout. Here's the MRI scanner where Dr. Alexander is graciously volunteered to volunteer for this demonstration. So we're acquiring some calibration and localizer scan. So this the first scan that we acquire is called a localizer, and this localizer basically allows us to see how the subject is positioned in the scanner, and allowing us to set up a reference for the rest of our scans. So we'll acquire a T1 weighted image, which we've discussed some within the class, and you'll see in just a second this scan you can kind of see here is 5 minutes long, where they have various different settings here on the console. So you can see that the scan plane is being acquired sagittally. The field of view is 25.6 centimeters. Slice thickness is 1 millimeter. You have the frequency encoding direction. The TR is 8.2 milliseconds. We have 160 slices that we're acquiring. You can kind of see this field of view here in this kind of turquoise box is that field of view. And you can kind of see that this field of view is appropriately covering the full brain. And I'm just going to try to position it, center it here in the brain. You can see the flip angle is 12 degrees. The TE or echo time is 3.2 milliseconds. This prep time, which is an inversion time for this particular sequence, is 450 milliseconds. And then the frequency and phase sampling is we're kind of acquiring 256 by 256 lines of K-space. So I'm going to get this started. You'll hear the scanner do a couple initial calibrations, and then you'll hear kind of what that scanner sounds like. And now it's scanning. You can see we have a countdown going here, so it's counting down from the 5 minutes. And in about 5 minutes or so, we'll have a T1 weighted scan of the brain. All right, that 5 minutes is over, and now you can kind of see here we have that T1 weighted image. I'm going to get this other scan started, and I'll show you a little bit more of this image. The next scan that we're going to acquire here is a T2 weighted image. Again, you see that the field of view here is set to be 25.6 centimeters with a slice thickness of 1 millimeter. Our TR now here is 3,000 milliseconds. And we have the echo time set to be at maximum, which in this case, you can kind of see if you hover over the variable, it's 93 milliseconds. And again, with 256 by 256 kind of lines of K-space. I'm going to get this started, and you'll again hear the scanner do some some calibrations, and you'll hear the this particular scan start, and you'll notice that it's quite different the way it sounds. And also note that this is a much faster scan, so it's about 3 minutes 22 seconds for it to be acquired. And there you go. So it's scanning right now. You notice that it's quite different sounds than the T1 weighted scan that we just acquired. Again, because those gradients are being played out differently than that T1. I'm gonna go ahead and lower that so that you can kind of still hear the scanner in the background. But let's go ahead and open that T1 weighted scan now. And what we can do is open this on a viewer here with the scanner, and I can adjust the windowing leveling. See if I can get a nice and there you go. So we have our T1 weighted scan now. So you can kind of see the white matter is nice and bright. Gray matter is kind of this intermediate gray level. And then the CSF is very dark and suppressed. It's a really nice image. You can make out really, different brain structures. The caudate here, the putamen, the thalamus is kind of here. You kind of see the nice detail in the corpus callosum, branching out to the genia of the corpus callosum in this case, branching out to kind of frontal white matter in the frontal part of the brain. You have the splenenium of the corpus callosum here, kind of projecting back out to the occipital cortex and posterior part of the brain. It's just overall a really nice quality, nice high resolution brain image. All right, we have about another minute left or so for the T2 weighted scan. And once that finishes up, we'll take a look at that one. Okay, the T2 weighted scan is finished up. I'm gonna get this fMRI sequence that we use up and running. So again, you can kind of see here on the console, we have a slightly smaller field of view at 22.4 centimeters, much larger slice thickness at 3.5 millimeters. A TR that's fairly quick, 2000 milliseconds. So every 2 seconds, we're acquiring an image, and we're getting 40 slices. With that number of slices, you can kind of see, because this is a 2D acquisition, you see kind of each slice laid out here on the console. That echo time is 25 milliseconds. We have a flip angle of 70 seconds. And our case-based sampling is much less than those structural images. This scan is set to be for 15 minutes long. We're not going to let this go this long just because you'll kind of get the idea of what these sound like and what the images look like here very quickly. So I'm going to go ahead and start this. Again, you'll have some pre-scanning done by the scanner. And you'll notice here and you'll soon see about every 2 seconds, a brain image is going to pop up here. And those are the individual fMRI scans. You can kind of see and make out that these are much lower resolution than the images that we have previously acquired from the structural images. About every 2 seconds, then a scan is going to keep popping up here until that full 15 minutes is done. And again, as Dr. Byrne and Alexander said in class, we're acquiring these data very rapidly so we can look at kind of fluctuations in the image of the signal that are related to blood flow. And we'll talk about that more in the course when we're covering fMRI. But it's essentially why we're wanting to acquire these images so quickly. I'm going to lower that a little bit, let that run for a couple minutes, show you quickly the T2 weighted scan here. So again, this image, so it's T2 weighted, so our white matter now, and this is a different, you can notice that this is a different orientation. We're now in a sagittal orientation, but our white matter now is a very low signal. Our gray matter is kind of the intermediate signal level, and then our CSF this time and free water is really bright. And it's just, again, because this is a T2 weighted scan, based on how how we acquired that data. This is with this specific imaging parameters. This is what we get. Again, very nice detailed image. Shows great contrast between gray white matter and CSF. Really nice detail in the microstructure. Again, you can kind of see the differences here in the cerebellum, and kind of see those kind of white matter branches branching out into the cerebellum. You can make out the brainstem really nicely. Here's the corpus callosum. Here it's very dark in white matter track. And again, you kind of make out these fine microstructure in the brain. So I'm going to go ahead and stop at this resting state scan. We're going to now acquire a diffusion weighted scan, another type of imaging technique that we'll talk about later in the class. Just again, so you can kind of hear what this sounds like. Again, note that the field of view here in this case is 23 centimeters. We have a slice thickness of 3.6 millimeters, but with a slice gap of negative 1.8 millimeters. Fairly long TR, so 9,000 milliseconds, acquiring across 76 slices. Our frequency and phase encoding, here you see that we did a 96 case base. And let me turn this up a little bit so you can again note it's somewhat similar to the functional imaging scan, slightly different in terms of the acoustics. We're still actually reference scanning. And there we go. So again, you'll start to see some images pop up here as we acquire them. One thing that you'll note, so these are T2 weighted scans. You can kind of see again, white matter is nice and dark. Gray matter is kind of the intermediate signal, and your CSF is nice and bright. So these images will continue to pop up here. One thing to note, so these are what we call non-diffusion weighted scans, so that we're currently not encoding diffusion. When we start to encode diffusion, you will hear that in the gradients, and it should just be coming up in just a second. See if you can notice the shift in acoustics. Okay, so shift actually just happened, so you can see that these images look slightly different now. And that is because we're starting to encode diffusion. Basically, the diffusion, by encoding diffusion, we get this kind of lower signal intensity. Particularly in areas of somewhat difficult to hear the shift in the gradients as more diffusions being created with this particular scan. So you can kind of hear those gradients shift right there. We're acquiring those diffusion directions as we learn when we talk about this, kind of this gets acquired in different directions, and it can be acquired at different strengths. And again, so you can kind of see these images are now even more different. We're actually encoding diffusion at a higher p-value here. So again, those images look a bit different. That diffusion weighting. All right, I'm going to go ahead and stop that scan. And that was our scanner demo for today. We'll catch you. We'll see you next time. Thanks.